Hello, let's continue making a 3D graphics engine.
And for this video we're going to start with the code as we left it in the previous part of this series, where we created a wireframe rotating cube. So let me just run that. There we go. That's what we ended up with at the end of the last video.
In the previous video I spent a lot of time deriving what's called the projection matrix, because I believe this is fundamentally the most important part of a 3D graphics engine, translating that 3D model information into 2D imagery on the screen. And before we get to full 3D world implementations, there are still some more fundamentals that we need to do, and that's what I aim to cover in this video.
Even though the rotating cube is very nice, it does actually show some things that we don't need in a 3D engine. Firstly, we can see the sides of the cubes we shouldn't normally be able to see. It's as if this is an ice cube. We can see right through it. So let's have a think about how we can remove the triangles that we can't see. Recall in the first video how we defined a cube. It was a set of 6 faces divided into triangles. And we took some effort to make sure that the winding of the triangles was consistent for the model of the cube. We in fact decided to do a clockwise winding. So the triangle consisted of this vertex, then this vertex, then this vertex. And though important, we didn't really go into the reasons why this was necessary. Well, 3D engines exploit two main things. Firstly, vertex geometry, as we've seen. But they also exploit the normals to the surface of the geometry. And it's important that we can create these normals. And just for the uninitiated, a normal is an imaginary line which is perpendicular to the plane that contains the triangle. Remember, a triangle is the most fundamental 3D primitive. It can only exist in a plane. So taking these two triangles at the front face of our cube, our normal sort of sticks out here. These ones at the side, it sticks out to the side. And the ones at the top, well, they point upwards. I don't need to draw all of these in, but I'm sure you can imagine that the triangles that we can't see, they also have normals as well. But it starts getting a bit clumsy to draw them on the screen. So I won't. Now our model doesn't contain any normal data. We're going to generate it as and when we need it. This will differ from 3D engine to 3D engine implementations. And as the engines become more sophisticated, you will in fact see that it is quite common to include normal information as part of the model. Fortunately, there are some geometric techniques for getting normals that are quite simple. Given two lines that are in a plane, the normal can be represented as a third line that is perpendicular to both of those lines. And fortunately for us, in 3 dimensions, there exists a mathematical function to generate this vector, and it's called the cross product.
And this is one of those times where we start treating parts of the 3D mathematics as black boxes. Deriving the cross product and what the cross product actually means is quite complicated, and I feel a little bit beyond the scope of this video, and in full honesty, a little bit beyond the scope of my understanding.
And indeed, if you check out the cross product on Wikipedia, you might be able to get a feeling as to why. Fortunately, we can treat it as just a black box. It will always give us the line that is perpendicular to the two other lines given to it. Essentially, each component of our normal vector is a calculation between the other two components of the other two lines. So the x component of our n vector, in this case, can be calculated as ay times bz minus az by. The y component, very similar, az bx minus ax bz. And finally, the z component, ax by minus ay bx. And this is why declaring our triangles in a consistent order was quite important. This triangle at the bottom of the screen is comprised of 3 vertices defined in a clockwise order. So algorithmically, I can get my A line by taking point 1 and subtracting from it point 0. and I can get my B line by taking point 2 and subtracting from it point 0. And so once I have my two lines, I can compute the cross product to give me the normal to the triangle surface. If, however, I didn't define these in a clockwise orientation, and instead did it the other way round, in a counterclockwise orientation, that's fine, but now when I calculate the cross product, the normal will go in the opposite direction. And this is completely acceptable, so long as we remain consistent in the ordering of our vertices per triangle. If we've created triangles with vertices in all sorts of different orders, then the normals computed from the cross product would be facing up and down, depending on the ordering of the triangle. And this may make, eventually, our shapes look a little strange. So I'm really just trying to enforce the point that consistency is key when creating the models. So why is the surface normal an important feature? Well, let's take a standard axis. We've got our x here, our y here, and our z going off into the distance. Crudely speaking, any of the triangles that have a normal whose z component is negative, we can see. Whereas those that have a normal that have a positive z component, we can't. So the normal of these triangles at the front may have the vector 0, 0, minus 1. But the ones at the back that we can't see, well, they'll probably be 0, 0, 1. And so knowing the z component, we can crudely optimize our cube to be consisting of only triangles that we can see. And we'll see shortly that this isn't entirely true, and we can do a better job. But let's implement this in code and see what happens. I'm going to calculate the triangle's normal after we have translated the triangle into world space, but before we do any projection. So we're still doing everything in 3D space. I'll create 3 temporary vectors. One, which is the normal, and 2 more that represent the lines. Calculating the lines is quite easy, and we've just seen it's just a case of subtracting the points from the triangle. So I'm going to take the translated triangle and take the first point, take its x component, and subtract from that the origin of our triangle, which we know will always exist as point 0. Naturally, I need to do the same for all components. And we're starting to see a bit of a theme here, that we're getting a lot of repetition.
And we'll talk a little bit more about how to reduce this repetition in the next part of this series, but for now I'm going to continue on in the manner that's familiar so far.
Calculating line 2 is equally as simple. Except now we want the different points. I've just shown that the normal is the cross product of the two lines, so I'm going to implement that directly. But there's something important to remember about normals, well, it's normally normal to normalize a normal, which means I need it to be a unit vector. So I'm going to calculate the length of the normal using Pythagoras' theorem, and divide the individual components of the normal by that length. The next section of code involved transforming the translated triangle from world space into screen space via the projection matrix. But I only want to do all of this if I can see the triangle in the first place. So I'm going to base doing this on the condition that the z component of our normal vector is less than 0. So I'll wrap it in an if block. Let's take a look. Well, straight away we can see some improvement. The triangles that are on the far side of the cube are definitely not visible. However, it's not quite right. We can still see that there are faces that we shouldn't be able to see.
And this is because we've not taken projection into account. We've got nothing that says where the eye is in world space relative to where that normal is. And traditionally, this is where we would introduce the concept of a camera. Now, cameras do add a lot of complication, and I'm going to commit the entire next part of this video series to just cameras. But for now, I wish to represent the camera as a vector location in space, and we're going to keep it fixed at 0, 0, 0.
To the main class, I'm going to add a single vector called vCamera, and this represents the position of the camera in 3D space, and this is an incredible simplification of how a camera will be implemented. For a start, there's no direction information. It doesn't imply which direction the camera is pointing. And so really, it's only acting as a bit of a placeholder for the next video. If we take a side-on view of the world, we can start to see what's causing this problem. So here I've got the eye point of the user, and we're looking from side on along the z-axis. And let's assume I've got my cube somewhere up here. If I draw normals onto my cube, we're filtering normals based on the z component. So in this instance, we can certainly see that the z component of the normal is less than 0, as is this one. However, this one is greater than 0. So we don't see these two faces at the back, but we do see the two faces at the front. The problem we've got is this face shouldn't really be seen, because perspective with the field of view shouldn't allow for that to happen. Because we're not considering where the surface is in 3D space relative to where the camera location is, we're assuming that all of our normals exist exactly on a plane directly in front of the camera. So that normal up there is actually really just some normal here, which of course we can see. This means that instead of just inspecting the z component alone, we need to look at the z component relative to the line of projection from the camera to the location of that normal in 3D space. So what we really need to detect is how much of the normal is in line with the imaginary line cast from the viewing position to the location of the normal. In this normal example, we can see that an angle there would be about 90 degrees, and we shouldn't be able to see it. We can see with this normal, the angle is certainly greater than 90 degrees, and we can't see it. But the one face that we can see, I've not even really got the room to put in the angle, shows that if it's less than 90 degrees, we can see it. This example is in 2 dimensions, but in 3 dimensions, working with degrees starts to get a little fiddly. But we can make a rash assumption that really what we're looking for is how similar is the surface normal to the line between the camera and where this normal exists. Unfortunately, when we're dealing with vectors, we have a function that can work out how similar two vectors are. And it's called the dot product. Now what's interesting about the dot product is it's a scalar value, a single number that tells us how similar two vectors are. And it's defined as being something like this. For three-dimensional dot product, it will look like this. AX times BX plus AY times BY plus AZ times BZ. And I think it is possible to see intuitively why this equation gives us a value of similarity between two vectors. If we make an assumption that A is equal to 1, 0, 0 and B is equal to 0, 1, 0, we know that actually these have nothing in common. One is in the x-axis and one is in the y-axis. They are not similar at all, which means this first component results in 1 times 0, so that's 0. The second component is 1 times 0, so that's 0. And the third component is 0 times 0, so that's 0. So the overall value of the dot product is 0. They're not similar. It makes sense then that if the two vectors are the same, we get a score of 1. But now let's assume that one of our vectors is actually indeed the direct opposite in one of the axes. Well, now our score is -1. So let's take a look at this little 2D example with our black main vector, and I'm going to test it against this red vector, which is pointing in the same direction. That, of course, will give us a dot product of 1. When they're not in the same direction at all, that will give us a dot product of 0. None of the original vector projects onto the new vector. And the final one, the green one, the vector's pointing in the opposite direction. This will give us a score of -1. And note, what I'm saying here assumes that the two vectors we're testing together have been normalized previously. Let's change the code so we're not just looking at the z component of the surface in isolation. Instead, we want to see how much of the z component of the triangle's normal is projected onto the line between where the camera is and the location of the triangle in 3D space. Let's start by simply commenting that line out. So I want to calculate the dot product between the line from the camera to the triangle and the normal. We'll take the x component first. The translated triangle's position, and we can take any point on this triangle because they all lie within the same plane. And from that we'll subtract the camera coordinate, which is 0, 0, 0. It might not be later on. So that satisfies the x component. We're going to need the y and the z components. Just do a little bit of code housekeeping here. And we're going to see if that is less than 0. Can we indeed see this triangle? Let's take a look. Well, that looks straight away much better. We now can no longer see any of the surfaces that shouldn't be visible. The reason we could choose any point on the triangle for where the normal is in 3D space is, of course, the triangle exists entirely in a plane. So the normal is pointing in the same direction for any position within that plane. I think this has successfully made the cube look rigid, but we can also test the theory. If we instead look for values that are greater than 0, we've effectively turned the cube inside out. Now we're only drawing the faces that are on the other side, and occasionally we can see it's drawing 5 faces. It's looking like an open box. But let's put that back.
Wireframe objects are very useful for debugging and seeing what's going on behind the scenes, but they don't really reflect a realistic solid body object in 2D space. So let's look at filling in the triangles now.
And I'm going to cheat a little bit here, because the console game engine has a routine called fill triangle. So I'm going to change our draw triangle to simply fill triangle. And let's take a look. Well, we can certainly see a shape rotating around on the screen, and the outline of it indeed looks like a cube, but because there's no sufficient shading going on the sides of the cube, our brains simply can't interpret what we're looking at. So we need to add a source of illumination. And I'm only going to bother illuminating the triangle if we can see it, because the more calculations that we're adding, the more expensive it's becoming to draw triangles. Now, the type of light I'm going to add is the most simplest form of lighting. It's a single direction light, and this sort of light doesn't exist anywhere in the real world. It assumes that all of the rays of light are coming in from a single direction, not a single point. So I've created a vector of 3D here, indicating the direction the light is shining. And you'll see, oddly, I've specified the Z component to indicate that the light is shining towards the player, and there's a reason for this. And that's, in our simple setup here, we can assume that a triangle is more lit the more its normal is aligned with the light direction. And we'll see in the next video that that's not quite true, but for this one it's sufficient to give us some clarity when trying to determine the shape of the objects. So having created a light direction normal, I also need to normalize it as we did before. I'm going to take the length of the light direction vector and divide it by that length. This allows us to play with interesting light directions without any consequence. And since we now have a method of determining the similarity of two vectors, it's called the dot product, I'm going to calculate the dot product between the normal of the triangle surface and the light direction.
Now, I have a problem with the console. I don't have a very high resolution of colours to choose from in order to do intricate shading. If you're implementing this engine using a platform that has RGB, fair enough, you can do what you need to do. But I have done this before when I looked at how I could implement webcam viewing in the console. We looked at colour algorithms. So I'm going to take some code directly from that would take a value from between 0 and 1 and convert it to a grayscale scheme that is suitable for the palette of the console.
And in the webcam at the console video, I created a function called getColor. And here it is. I've just literally cut and pasted it in directly. It takes the floating point luminance value between 0 and 1 and returns the symbol and console colour combinations that reflect that luminance as a mixture of black, grey and white character colours, but also different shadings of the pixel. Because if you remember, we emulated colour by mixing together different intensity pixels. On the console, we don't have RGB, we're using colour combinations and character combinations. So I'm going to store the symbols that represent the colour for the triangle. And since my entire triangle will be shaded the same way, I only need to store these per triangle. We may consider looking at storing these per vertex in a future video. Going back to the lighting equations, I can now extract the symbol and character information required to represent a particular shade of grey in the console. Simply by looking at what the dot product value is. And I'm going to set the values of my triangle's colour and symbol to whatever is returned by this function. But please remember, this is really console specific stuff. If you're doing this not on a console, then it's much simpler. Just choose the colour as you need to. We've just set the colour and symbol values of the translated triangle. We're now going to transform that translated triangle into a projected triangle. So I need to make sure that that information gets carried on through too. That's just a simple case of copying them over. You might think, well, why didn't I just do this in the first place? But I'm trying to encapsulate functionality so that the flow is easy to follow. And as the engine develops in sophistication, we'll be glad for these boundaries of encapsulation. When we get to the point where we're drawing the triangle on the screen, instead of choosing a solid pixel that's coloured white, we can now use the symbol and colour information that's associated with the projected triangle. However, I'm just going to copy and paste this code and change it back to draw triangle. I just want to back this up for later. So let's change pixel solid to try projected dot symbol, and we'll change the colour to try projected dot col. Let's take a look. And now we can see that the cube is illuminated with a light that looks like it's emanating from where the player is. One of the reasons I wanted to keep this line is it's very useful for debugging. We can fill the triangle, but if I set this to FG black, or indeed any other colour, I can now fill the triangle and draw the triangle so I can see the wireframe outline of the cube. This could be quite useful for debugging.
Let's face it, cubes are a bit boring, and especially games made from cubes, they're incredibly boring. So I could sit here and go through algorithms to generate spheres and cylinders and other interesting shapes to draw on the screen. But I know that's not really what any of you want. What we want is spaceships, laser sharks and mecha unicorns. So let's look at how we can implement third-party objects into the game engine.
So far we've manually crafted the cube, and this is quite time-consuming and laborious, and even for a simple shape it's surprising just how much data you need. A slightly more sensible approach would be to use some 3D modelling software, create the model and export it into a format that is easy for our game engine to read. Unfortunately, there is such a format. It's called the OBJ or object format. You can download object files from the internet. There's quite a few different repositories full of interesting shapes that have been modelled before. But it's also very easy to make your own in software like Blender. Blender is free, I like it, it's very powerful and very competent software. So here I am, very quickly building up a spaceship model for exporting to our game engine. One of the nice things about Blender is you can visualize the normals, and so I'm checking to make sure that the normals all point outside of the model. This will ensure that our triangle winding order is consistent across the model. But I won't be exporting this normal data as part of the object file. It's important that the model consists solely of triangles. That's because our game engine only understands triangles. However, object files are oblivious to actually how many points make up the surface polygons. When we export the object file, I don't really care about any of the other properties. I just want the vertex data and the face data. But I want to make sure, just in case I've missed some, that it automatically triangulates the faces for me. Now, one of the nice things about object files, and one of the little hidden secrets in Visual Studio which not many people know, is that if I take the object file that we've just created and drag it into Visual Studio, it does indeed render it. And you can drag it around. I think this is quite nifty. Regardless, we're going to build our own loading code to load the model from the file into a format that's more sensible for us. I feel the best place to do this is in our mesh structure. So I'm going to add a function called load from object file that takes a file name and returns whether the file was loaded successfully or not. Let's have a quick look at what's inside an object file. You can see it's in a human readable text format, so that's useful. The first two lines look like comments and junk, and that's indicated by the hash symbol at the start of the line. The next few lines start with a lowercase v, and this indicates vertex. This is the location of a single vertex in 3D space, and we've got quite a few of them. We have a line here, S off. I've no idea what that means, so I'm going to ignore it. And then the next few lines, they begin with a lowercase f, which stands for face. And in this case, we can see that the face consists of 3 points. And that's great, because that means it's a triangle, and all of our faces are triangles, so we can interpret this line as being a single triangle in our graphics engine. And the way this works is we'll build up a pool of vertices from these lines here, and these numbers are the indexes into that pool as to which vertices we want. This means we only need to record each vertex once, but we can reuse it in other triangles, so it's quite an efficient form of storage. As we read through all of the triangles, we get to the end of the file, and it stops. So this should be quite a simple thing to do. I'm going to need some file handling functions, so I'm going to include fstream and stringstream. And simply, I'm going to open the file first. If I can't open it, I'm going to return false. It means the file can't be found. I now need to create that temporary pool of vertices. So I'm going to create a vector of my 3D type and just store that locally for now. That will disappear once we've finished loading the object, because the mesh itself will store the triangles at the end. I now want to iterate through the file extracting the data, but I don't want to read from a file that has no data left. So I'm just going to make sure that I've not hit the end of the file. I'm going to make a dirty assumption here that one of the lines of the file doesn't exceed 128 characters, and I'm going to use the getLine function to read the whole line in one hit. It's a little inconvenient these days to work with character buffers, so I'm going to turn the line into a string stream. And I can populate the stream in the same way that you would use cout. If we look at the file again, we can see that each line always starts with a character that describes what the line is. As I read from the string stream into variables, I'm going to need somewhere to put this character, even though I might not be interested in it. So I'm going to create a temporary variable called junk. It's a single character. Let's check to see what the line begins with. If the character is a V, then we know we're reading in a vertex. In that case, let's create a temporary vertex, and because we've got everything in a nice string stream, we can allow the standard library to really make all of this very easy for us. So the string stream S, I'm going to read in the character at the front. We know that's going to be a V in this case, but we can consider it junk. I'm not interested in it, but I am interested in the 3 next values, which we can read directly into Vx, v.y, and v.z. Once we've compiled the vertex, I'm going to add it to our temporary pool of vertices. And that's it. That's all that's required to read in the vertex information. In a similar way, if the line begins with an F, I know really what I'm doing is making a triangle. So I'm going to be reading in 3 integer values, and exactly the same way I read in the vertex data, I'm going to read in the junk character, which in this case is F, and populate my array here with the 3 vertex indices. And in a single hit, I'm going to construct the triangle and push it to the triangle belonging to the mesh. So let's have a look at this line. So this is the tries variable, which belongs to the mesh, consisting of a vector of all of the triangles that the mesh is comprised of. I'm going to add to that vector the 3 triangle locations, but these are stored in my temporary pool of vertices. So this is point 0 of my triangle, point 1 of my triangle, and point 2 of my triangle. You'll see that I'm indexing the temporary pool of vertices with the face ID value. But I'm subtracting 1 from that, and that's because, rather frustratingly, all of the information in an object file starts counting from 1 and not 0. And that's great. That's all the code I need to read in an object file into the triangle structure of my mesh. Let's waste no time in trying this. So instead of defining the cube as a bunch of vertices directly, I'm going to comment that out. And instead, even though it's called cube, and now it's going to be a spaceship, I'm going to use our load from object file function, and I'm going to load the object file, videoship.obj. Normally you would test for errors, but I'm not going to. Let's take a look. Well, that's very nice, but, oh dear me, all sorts of things going horribly, horribly wrong here. It kinda does look like the ship, but it's a mess. What's gone wrong?
Well, 2 things are happening here. The first is we're not drawing our triangles in the correct order. So that means we're actually drawing triangles that are further away on top of triangles that are closer to the user. So this makes the model look a bit like a mess. The second problem we've got is a little less simple. And we'll solve it with a hack for this part of the series, but we'll actually solve it properly in the next video. And that is that as the triangles approach the camera position, if you remember as part of the projection, we divide them by the Z value. Well, this Z value gets smaller and smaller and smaller, and indeed tends towards 0. So this means when we're drawing the triangle, the X and Y values get much, much, much bigger. And we saw, as the ship was rotating, it was stuttering because there was not enough performance of the computer to actually draw a triangle which is so huge in the time that we would expect it to. To solve that problem, we would need to implement clipping, and we'll do that next time. But for now, what I'm going to do is position the ship far enough away from the camera that we know that none of the triangles are going to go too close to the camera.
We already offset the cube, now the ship, into the distance using this translation procedure here. But we only offset it by 3. To push it further away from the camera, I'm going to offset it by 8. So now let's take a look. We should certainly see it'll still look like a mess, but we don't have any performance inconsistencies anymore because none of the triangles get drawn behind the camera. And now that it's running smoothly, we can start to see, yes, the triangles that are visible because of the surface normal but are behind other triangles are still being drawn. And this is a problem.
In a normal 3D engine, we would have something called a depth buffer, and that is where every pixel on the screen also has a Z value associated with it. So when we want to draw a new pixel, we test that pixel against the value that's already in the depth buffer, and if it's in front of that pixel we draw it, and if it's behind it we don't, we can't see it, and that's great. Being in the console, I don't have that luxury. So instead what I'm going to do is take the midpoint value of a triangle's, take the Z component of that midpoint and sort the triangles based on that value, and we'll draw them from back to front. This is called the painter's algorithm. So we draw the things that are furthest away first and draw the things that are closest to the camera last.
And this means we need to change the structure of our code ever so slightly. So far we've both translated, transformed, projected and drawn our triangles in a single loop. Instead, what I'm going to do now is accumulate the triangles that we want to draw into a new vector. And we know which triangles we want to draw because we've already culled the triangles we can't see, and we've illuminated them, and we've performed a projection. But instead of drawing them straight away, I'm going to add them to this vector. So I'll get rid of this draw code. Now that I have a vector of triangles that I need to raster, I'm going to come out of my main loop and create a little auto for loop which goes through all of the triangles in that vector and draws them. This gives me a little space in between to sort the triangles. And fortunately, thanks to the algorithm component of the standard library, they provide a sort function for us, rather than writing our own, which will never be as efficient as those that have been tried and tested by experts. I'm just going to use the sort function from the algorithm library and modify it slightly for our needs. So let's add in some sorting code. The function is simply called sort, but we need to give it a starting point in our vector. Triangles to raster dot begin. We need to give it an ending point. Triangles to raster dot end. And now we need to give it a sorting criteria. Now, a triangle isn't just a number. So it allows us to put in a little lambda function to actually implement the sorting criteria for us. And it's going to test two triangles each time, T1 and T2. And I'll just put this little lambda on the line like that. There we go. Very pretty. So we want to get the midpoint z values of both triangles. This will only give us an approximation, so we may still see the occasional glitch, but I was surprised at just how well this works. And the midpoint is quite easy. We take the 3 points that make up our triangle, we take the z components of them, and we average them. So we do that for triangle 1, we do that for triangle 2, and the lambda function is expected to return a boolean as to whether it should swap the positions of the two triangles. In this case, we're doing it if z1 is greater than z2. You may need to play around with the polarity of this to get it right. So now we have a single loop which does the bulk of the transformations to sort out which triangles we want to send to our rasterizer for drawing. We're sorting those triangles so that they're drawn in the correct depth order, and then we're going to actually raster the triangles to the screen. I'm not going to draw the wireframe outline, so let's take a look. And I think that's quite pleasing. We've now got an illuminated, optimized model being rendered to the screen, and you can see that our Z sorting method on the whole works very, very well indeed. It is a hack, so there will be some slight imperfections, and I think you can just see them on the edges of the wings, but on the whole I'm pretty pleased with how that's come out.
And so that's that for this video. Now you might be thinking, well hang on, that's not been very much. But what we've established here is the very basic foundation of a 3D engine, because in the next part of this series we're going to be looking at how do we move the camera around, how do we start implementing 3D worlds, and this becomes quite complicated. And that's where we'll be looking at implementing the view matrix, which represents the camera, so we can put the camera at any point in the 3D world in any orientation. And we'll also be looking at clipping, which is quite an important way of optimizing which parts of the triangles get drawn. As we saw in this video, if the triangle goes beyond the edges of the screen, it starts to cause problems for the rasterizer because the triangles become too huge. How do we cut down the triangles in order to make them fit into our world? There'll be one other thing that we'll be looking at in the next video too, and that is optimizing all of this redundant code. So far you've seen me do everything on the X component, then the Y component, then the Z component. I feel that this is starting to become a little bit of a bottleneck for productivity. So we might look at either creating our own or using an existing matrix vector library to do this. Anyway, as always, the source code is available for this on GitHub. Come and have a chat with us on the Discord server. If you've enjoyed this video, a big thumbs up please. Have a think about subscribing, and I'll see you next time. Take care.